Hi, in this short video I'd like to show you how to do two Hardy-Weinberg problems. If you want to go ahead and pause the video here and work on the problem yourself, go ahead. And now that you've worked on it, let's go ahead and go over the solution. This is similar to the other problems that we did earlier this year. I think the first thing you have to do is figure out the total population size, and according to my calculations it is 1082. The first thing I do is I always try to solve for q, or q squared. In this case, q squared is going to be equal to 835 divided by 1082. And the reason is because we have 835 finches that are displaying the recessive phenotype. Now when you type that into a calculator, you're going to get something like 0.80910, and the number keeps going. If that's q squared value, then to find q you would take the square root of this value, and the square root of 0.80910 is going to be 0.8995 and a few other numbers beyond that. To solve for p, I would take 1 and subtract this number from 1, and I'm going to get a p-value of 0.1005, because remember that p plus q always equals 1. Now the question is asking me how many finches are heterozygous. Heterozygous would be this genotype here. To figure out the number of finches that are heterozygous, it's going to be 2 times p times q, or 2 times 0.8995 times 0.1005, and that is going to equal, I believe it's 0.1808, and then a few numbers beyond that. You take this number here, 0.1808, multiply it times the total number of finches in the population, 1082, and you're going to end up with a number of 196. And that's my answer. There are 196 finches that display the recessive phenotype. Now, depending on what numbers you rounded these to, whether you rounded it to the thousandth or the 10,000th, you're going to get some number between 195 to 197. And on the test, I will always accept a limited range of answers. Now, this second Hardy-Weinberg problem is different than the ones you've seen before. In this one, we don't have to do quite as much calculation as you would think. If you want to pause the video here and work on this problem, go ahead. And now that you've had a chance to look at this, let's look at the solution. It says a population of squirrels is in Hardy-Weinberg equilibrium and they have equal allele frequencies. Well, at this point you need to understand that what that means is that the p-value is 0.5 and the q-value is 0.5. It says a river splits the population into two smaller populations. Well, now that we have smaller populations, we're no longer going to be in Hardy-Weinberg equilibrium. So we would expect these numbers to change. Now I don't know which value is going to go up and which value is going to go down, but they should change. It says a scientist came along 50 years later and sampled a population of squirrels on the southern side of the river and found that 38% demonstrated or showed the recessive phenotype. So 38% of them are homozygous recessive. Well, that makes things a little bit simpler. That means that our q value, or our q squared value, is going to be 0.38. To solve for q, all we have to do is take the square root of 0.38, and according to my calculations, that would be something like 0.61644. And now we have to compare this q value to our original q value, because let's look at what the question is asking. The question is asking, what is the difference in the recessive allele frequency over that time period? Remember, q is the recessive allele frequency. Our q was 0.5. Our q is now 0.61644. The key word here is what is the difference. That means that we're going to subtract. So I'm going to take my new q value of 0.61644. I'm going to subtract the original q value of 0.5, and that's going to give me an answer of around 0.12. And that's if I round it off to the nearest hundredth. On the test, I will always tell you what value to round off to. In this case, the nearest hundredth would be 0.12. So those are two Hardy-Weinberg sample problems, and I hope that's helpful. Let me know if you have any questions, comments, or concerns.